NMR, or nuclear magnetic resonance spectroscopy, is by far the most important spectroscopic technique for determining the structure of organic compounds. So what kind of information can we get out of this technique? What makes it so great? Well, the element most commonly observed by NMR is hydrogen. And that is very useful to organic chemists because hydrogen atoms are very abundant in organic molecules. So this introductory lesson is going to be very much a big picture lesson. And then in subsequent lessons, we will drill down and look at each of these points in a lot more detail. So depicted here is the NMR spectrum of a simple molecule, namely ethyl bromide. So the first thing you should see in the NMR spectrum is that you get positive peaks coming off of a baseline that's at the bottom of the spectrum. On the bottom is a scale. There's the Greek letter delta on the bottom of the scale, and then it says next to that ppm, which stands for parts per million. And then this scale, 0 is on the right side, and numbers increase to the left. This particular spectrum only goes as far as 8 parts per million, and many molecules have all their peaks in this region between 0 and 8, but in some cases we have to expand the scale a little bit further to the left. So from an NMR spectrum, we can determine 5 things about a molecule. And again, as I said, each one of these we're going to go into in more detail in subsequent lessons. But first of all, you can determine how many different types of hydrogen there are in the molecule because there is a peak in the spectrum for each type of hydrogen. And by type of hydrogen, I mean chemically indistinguishable hydrogen atoms. So in this molecule, in ethyl bromide, there are 2 types of hydrogen. You have the 2 hydrogens on the carbon bound to the bromine, and then you have the 3 hydrogens on the terminal methyl group. The 2 hydrogens on the carbon bound to the bromine are the same. There's nothing that in any way can differentiate them because of tetrahedral geometry around that carbon. Similarly, the 3 hydrogens on the methyl group are the same. Thinking back to the discussion of elimination reactions, though all 3 of those hydrogens on the methyl group are beta hydrogens, so any one of them would be equally capable of being removed by a base in an elimination reaction. So in molecules like this, that are just straight chain molecules that have one functional group on them, different types of hydrogen are generally going to be the hydrogens on different carbons. We will, however, see some examples of molecules that have symmetry, where you can have hydrogens of the same type that are on 2 different carbons, as long as those carbons are related somehow by symmetry and the same distance from a functional group. There are even more complex cases that we will not cover in this introductory course, where you can have hydrogens on the same carbon that are inequivalent. Just know that that's out there if you might continue and study more chemistry in a higher level course. So getting back to this molecule, you can see that the CH2s are labeled A and are in blue, the CH3s are in pink and labeled B, and if you look at the spectrum, there is a blue peak labeled A, so somehow that peak is due to the CH2s, and there is a pink peak labeled B, which is due to the CH3s. 2 types of hydrogen, 2 peaks. The second thing you can figure out is how many hydrogens there are of a particular type, because the area of a peak is proportional to the number of hydrogens of that type. Okay, so area under a curve should take you back to the thought of calculus. You know, integral calculus is about determining the area under curves. Luckily, you don't have to do any calculus to be able to interpret an NMR spectrum, because computers are very good at doing that for you, and the computer will measure the area under the curve and spit that number out at you. So in this case, The peak labeled B is 1.5 times as large in area as the peak labeled A. And that is consistent with the fact that there are 3 hydrogens of type B and only 2 hydrogens of type A. Thirdly, an NMR spectrum will tell you very clearly if there are any hydrogens located on a double bond or an aromatic ring. So exactly where a peak is located along the x-axis gives you a lot of information about what's nearby. The fourth point is if any electronegative atoms are located near a particular hydrogen. We'll go into all of this in a whole lot of detail, but in this molecule you have no double bonds, no aromatic rings, so we have no peaks in those regions of the spectrum. But you do have a bromine atom, and the hydrogens that are near the bromine can also be found in a particular region of the spectrum. So in a subsequent lesson, I'll give you a chart as to where you would expect certain types of hydrogen based on whether they're on double bonds, aromatic rings, or near electronegative groups. Finally, and this is in many ways the most important thing you can get out of an NMR spectrum, is you can find out how many hydrogens there are on the adjacent carbon atoms to the hydrogen being observed. And the way we're going to figure this out is by looking at how many lines a particular peak is split into. So you can see that the pink peak labeled B is actually split into 3 lines, and the blue peak labeled A is actually split into 4 lines. That is giving us information. The fact that the pink peak is split into 3 lines is telling us that there are 2 hydrogens on the adjacent carbon. The fact that the blue peak is split into 4 lines is telling us that there are 3 hydrogens on the adjacent carbon. Again, we'll flesh all of this out in a subsequent lesson where we go over that in greater detail. Before we go any further, however, about the interpretation of spectra, what I want to do is spend a lesson talking about what is nuclear magnetic resonance, what happens to the molecule, and how do we get a signal that we can record in a spectrum at all. So that will be the subject of our next lesson.